Hello and welcome to Module 3, Concept Generation, Functional Analysis, System Architecture, and Design. This module we will talk about applying functional analysis and allocation conceptual design. First of all, we need to start with what is the purpose of functional analysis and allocation. The objective of this functional analysis and allocation task is to create a functional architecture that can provide the foundation for defining the system architecture through the allocation of functions and subfunctions to hardware and software and operations, in this case operations being personnel. Referring back to figure 2.4 from Blanchard and Fabricki, the functional analysis is an essential element of the early stages of the life cycle. It refers to the iterative process of translating system requirements into detailed design criteria. It also includes the identification of resources required for system operation and support. So what is the scope of functional analysis and allocation? Well, first of all, functional analysis and allocation is the examination of a defined function to identify all the subfunctions necessary to accomplish of that function. The subfunctions are arrayed in a functional architecture to show their relationships and interfaces, both internal and external, and upper-level performance requirements are flowed down and allocated to the lower-level subfunctions. So again, going back to a function, what is the purpose of a function? A function is a characteristic, task, action, or activity that must be performed in order to achieve a desired outcome. Essentially, it is what the system is intended to do. A function may be accomplished by one or more system elements comprised of equipment, such as hardware, firmware, facilities, personnel, procedural data, or software. Certainly there are others, but this accounts for the vast majority of them in the instances that we're talking about here. So looking at a top-down system, XYZ, from the Blanchard and Fabricki book, this function breaks down system into components. At the very top level is the system XYZ, and at the lower level, right below that, are different components. In this case here, you have the system operator, the equipment, the computer resources, or the facility. Further breaking down those, just picking the equipment, you can break those down into units within the equipment, and then even just different assemblies within each unit. One of the key deliverables of functional analysis is the functional baseline. The baseline is completed at the end of conceptual design and culminates in a complete set of requirements that all lower-level requirements can later evolve from. The functional baseline in conceptual design will eventually be the lead into the allocated baseline during the preliminary system design. Another key deliverable of functional analysis is the system specification. This occurs after requirements analysis, trade-off studies, and evaluations. It is one of the very final steps just before the conceptual phase design review. System specification includes the technical, performance, operational, and support characteristics for the system as an entity. It also includes the allocation of requirements of functional areas and defines the various functional area interfaces. The information derived from the feasibility analysis, operational requirements, maintenance concept, and functional analysis is covered here. So next, what is the scope of functional analysis allocation? This activity should be conducted to define and integrate a functional architecture for which system products and processes can be designed. A functional architecture is an architectural model that identifies system function and their interactions. It defines how the functions will operate together to perform the system missions. Functional analysis and allocation must be conducted to the level of depth needed in order to support the required synthesis efforts. Identified functional requirements must be analyzed to determine the lower level functions required to accomplish the parent requirement, and all usage modes must be included in this analysis. Again, the purpose of functional analysis is to be able to prevent the system's functional architecture. Functional requirements should be arranged so that lower-level functional requirements are recognized as part of the higher-level requirements. Functional requirements should be arranged in their logical sequence, meaning that their input, output, and functional interface requirements defined and be traceable from beginning and end conditions. And time-critical requirements must also be analyzed. So let's look at this a little bit deeper here. Traceability is very important from beginning to end conditions, both for understanding the need for the functional requirement as well as potential changes. When changes get made down the road, you may have to go back and ask the question of why those were made or why the decisions were made as they were. And that's why traceability to the decision up front at this stage when you're putting them together is very critical. Now let's even look at what a functional requirement is. A functional requirement is any requirement which specifies what the system should do. In other words, a functional requirement will describe a particular behavior or function of the system when certain conditions are met. For example, send an email when a new customer signs up, or open a new account. Conversely, a non-functional requirement is any requirement which specifies how the system performs a certain function. In other words, a non-functional requirement will describe how a system should behave and what limits there are on its functionality. Non-functional requirements generally specify the system's quality attributes or characteristics. For example, data should be batched and updated for access within 24 hours. So, in summary, a functional requirement is the what, but a non-functional requirement becomes the how. Functional analysis and allocation should be conducted iteratively. This is important to define the successively lower-level functions required to satisfy higher-level functional requirements and to define alternative sets of functional requirements. With requirements analysis to determine the higher-level requirements are satisfied, and to flow down performance requirements and design constraints. It's impossible to overstate the importance of conducting functional analysis and allocation as an iterative process. As it continues to develop, it is important to react and update other functional requirements as necessary. The alternative of keeping development static will invariably lead to surprises at the back end, including longer development time and sub-optimization of your total system. Trade-off studies should be conducted within and across functions to support functional analysis and allocation of performance requirements and evaluate alternative functional architectures. This goes right along with the iterative nature we just discussed. The trade-off analysis will involve synthesis. Synthesis refers to structuring the respective components to create a feasible system configuration. In order to do this, requirement trade-offs will likely be necessary. Input criteria. What do you need to know to start functional analysis and allocation? The more that is known about the system, the better. Obviously, that is the case up front, where you'd like to know as much as possible. But the reality is you only know so much, and so you have to accept what you have to know. At the same time, identify as much as you can know early on. Ideally, functional analysis and allocation should begin only after all the system requirements have been fully identified. Often, of course, this will not be possible, and the task will have to be done iteratively, with the functional architecture being further defined as the system requirements evolve. This means that the requirements analysis must be completed before this task starts. The functional analysis and allocation task should help to reveal any missing requirements and help to refine or clarify others. Representative inputs from the user or customer in program management are customer needs, objectives, requirements, technology base, program decisions or requirements, such as objectives to reuse certain hardware and software, specifications and standards requirements, or concept of operations. Now let's look at output criteria. What is the output from the functional analysis and allocation effort? The successful completion of the functional analysis and allocation effort will allow the start of the system synthesis phase at the systems engineering process. The final criteria for completion of the functional analysis and allocation effort is the complete problem definition. This is the process where the functions to be performed by the mission are identified and the requirements that define how well these functions must be performed are generated. This is a key milestone within the systems engineering process. Output products must relate the sequence of the functions that have to be performed to satisfy the mission needs to the specific system requirements. They must also reveal any timing relationships that are key to mission success. And lastly, the performance and quality requirements that specify how well these functions must be performed should be traceable to those system requirements, as well as the mission needs and the constraints that may be placed upon the system by the customer, community, or legal requirements. Certainly, legal and regulatory requirements are always going to be present, but the larger the system is, the more likely it is to have government and or legal interactions or requirements holding up certain elements and that the system has to conform to. There are various formats that the output of the products of the functional analysis and allocation task can take, depending on the specific stage of the process and the specific technique used to develop the functional architecture. Below are several, and let's go through them individually. Behavior diagrams describe behavior that specifies system-level stimulus responses using constructs that specify time sequences, concurrencies, conditions, synchronization points, state information, and performance. This notation provides constructs for control flow, data flow, state transition, and state machine characteristics of the system. Context diagrams are top-level diagram of a data flow diagram that is related to a specific level of system decomposition. This diagram portrays all inputs and outputs of a system, but shows no decomposition. Control flow diagrams are a diagram that depicts the set of all possible sequences in which operations may be performed by a system or software program. There are several types of control flow diagrams, which include box diagrams, flowcharts, input process output charts, state transition diagrams. Data flow diagrams provide an interconnection of each of the behaviors that the system must perform. All inputs to the behavior designator and all outputs that must be generated are identified along with each of the data stores that each must access. Each of the data flow diagrams must be checked to verify consistency with the context diagram or higher level data flow diagram, just to ensure the overall synchronization. Data dictionaries. Documentation that provides a standard set of definitions of data flows, data elements, files, databases, and processes referred to in a data flow diagram set for a specific level of system decomposition. This is an aid to communications across the development organizations. State transition diagrams. A diagram that shows the possible states that are possible and the way a system may change from one state to another. The systems used are circles that indicate system states and line segments that indicate how the change from one state to another can occur. Entity relationship diagrams. These diagrams depict a set of entities, functions, or architectural elements, and the logical relationship between them. The attributes of the entities can also be shown. Functional block diagrams. These block diagrams relate the behaviors that have to be performed by a system to each other, show the inputs and outputs, and provide some insight into flow between the system functions. Models. Models are abstractions of relevant characteristics of a system used as a means to understand, communicate, design, and evaluate, including simulation, a system. They are used before a system is built and while it is being tested or in service. A good model has essential properties in common with the system and situations it represents. The nature of the properties it represents determine the uses for the model. The model may be functional, physical, or mathematical. Timing analysis requirements. The results of the analysis of time required to perform concurrent functions that provide inputs to a subsequent function. They provide an assessment of the time that the system will require to accomplish a desired output behavior when concurrency of functions has to be considered. Simulation results. The output from a model and the system that behaves or operates like the system under interest when provided a set of controlled inputs. Functional and concurrent thread analysis results. The output of a system or model that demonstrates a specific sequence of functions of interaction system objects. A system's overall behavior is the time response of all of its threads to initial conditions, its environment, and control mode parameters. And lastly, IDEFO diagrams. These are process control diagrams that show the relationship between functions by sequential input and output flows. Process control enters the top of each represented function, and lines entering the bottom show the supporting mechanism needed by the function. IDEFO is an acronym for Integrated Definition. There are various formats to the functional analysis and allocation task. These various output products characterize the functional architecture. There is no one preferred output product that will support this analysis. In many cases, several of these products are necessary to understand the functional architecture and the risks that may be inherent in the subsequent synthesis of the system architecture. Using one or more than one of these formats allows for a check and balance of the analysis process and will also aid in the communication across the system design team. While you don't need to use all of them, it is a good practice to use more than one.